Biology, Chapter 21. They call it Incoming Substances, and this looks at the respiratory system and the digestive system. So here we go. First of all, the respiratory system. We start kind of at the you know the beginning, as it were, of the respiratory system and look at the nasal cavity. And so you have a diagram here that has some of the main parts that are going on up in this part. So the nasal cavity would be this cavity up along in here. Okay. And it is separated from the oral cavity by the palate. And what you cannot see, well, I mean, I guess you can kind of see in this diagram. Picture like the back wall here, as it were, uh, that runs from front to back and top to bottom. Okay. That is the nasal septum, and what it does is it separates your nasal cavity into the left and right sides. So, like just like how your nose has a left nostril and a right nostril, and imagine that cartilage that separates your left and right nostril extends back farther into your head and becomes a little bit thicker and a little bit more firm, and that's the nasal septum. And you've maybe heard of a thing that happens sometimes when babies develop in the womb called a cleft palate. That's similar to this, where except that's dealing with the palate here, where the palate starts forming like a left side and right side, and then they merge together and fuse and becomes one plate, as it were. But sometimes when baby's developing in the womb, the left and right sides don't fully reach each other, and they end up with a gap between. And so what that does is it allows it makes it so that the nasal cavity and oral cavity are not fully separated from each other like that. And then it also results in something called a hair lip, um, where it's like their lip has a little indentation where the palate didn't fully join. And surgeries now do can do a really good job of gradually repairing that and making it so that you can't really tell anymore. But anyway, so yeah, that relates to the palate. And then palate is I guess since I'm talking about the palate. The palate has two parts: the hard palate and the soft palate. The hard palate is up here. Think of like the roof of your mouth, and then the soft palate is this part down here. And the soft palate ends in the little dangly thing at the back of your throat. That's called the uvula. The uvula. That's the dangly thing at the end of the soft palate. And the uvula serves the function of different times it will extend up like this. And when you're swallowing, for example, the uvula closes this opening here, and it makes it so that the food that you're swallowing doesn't go up into your nasal cavity and instead is forced down your esophagus. So, very handy. And then ciliated mucous membrane. This is just generally talking about what kind of membrane lines the nasal cavities. It says lines the nasal cavities and filters bacteria, smoke, and dust particles from the air. The air in your nasal cavity also gets warmed and moistened a bit so that when you breathe in through your nose, you are getting air that has been partially filtered and air that has been warmed a little bit and air that has been moistened a little bit or humidified. And all of three of those things make the air a lot more suitable for going into your lungs. When you breathe in through your mouth, you lose a little bit of that. The air still gets warmed and moistened, but it doesn't get filtered as well when you breathe in through your mouth. And there's a homework question that talks about tracheotomy, and a tracheotomy would be where they put a hole right around here, and the person breathes directly in through their throat. Now, there's some medical reasons why this would be done sometimes. Usually involves people who've done a lot of damage through smoking. But tracheotomy can also be an emergency procedure if a person is suffocating and whatever is lodging their air pipe, maybe like right there, the larynx opening into the pharynx, whatever is lodged right there, the cannot get dislodged, and they don't have a better way of dealing with it. And they've tried the Heimlich maneuver, and nothing seems to be working. Kind of an emergency procedure that could be done is to create a hole there directly through the throat into the larynx. But the downside of breathing like that for any kind of long term breathing is the air is not getting filtered, moistened, or humidified and warmed. And so it's just not quite as ideal air for getting into your lungs. Okay, so that's that. And then the pharynx. This is like this upper part of the throat. It extends from the nasal cavity to the esophagus. So the nasal cavity end would be right there. So you have the label there, the pharynx, and then down to the esophagus. So roughly right there up to there would be the pharynx. And there are a variety of openings that the pharynx has, a total of seven, two, four, five, six, seven. You have two openings that go into the nasal cavities because you have a left nasal cavity and a right nasal cavity, and that allows for airflow from the nasal cavity down in toward your lungs. You also have two passageways in your pharynx that go out to your middle ear, and those are called your eustachian tubes, and they help equalize the air pressure in your ears. So, for example, like if you go on an airplane, or if you even just uh, a lot of people just driving up to Auburn, for example, would feel that kind of pressure in their ears, and that's because the pressure inside the ear is no longer matching the air pressure outside because the air pressure outside has changed. And we have these little tubes that go from inside the ear down and open into the back of your throat, and they allow for the air pressure inside your ear to be adjusted. So that's where yawning or chewing or eating something or like holding your nose and blowing, all of those things can be different ways that help those eustachian tubes do the job of making the pressure inside your ear match the pressure outside your ear. Then we have one opening to the oral cavity. So that would be like there, and that allows food to go down to the stomach. And then one opening to the esophagus. I'm sorry, one opening to the oral cavity. Oh yeah, okay. Yeah, so that's there. That's there. I was looking at the wrong thing. So the nasal cavity into the oral cavity. So the opening of the pharynx with the oral cavity would be allowing food when you're eating or air if you're breathing through your mouth to get into the back of your throat. One opening to the esophagus, that's allowing food down to the stomach, and then one opening to the larynx, and that is allowing air down into your trachea to go down into your lungs. All right, then we have something called the larynx, also known as the voice box. And what it is this two mucous membrane vocal cords or vocal folds. You'll see both terms sometimes, and it's basically kind of a thick band of muscle, and you have two different ones. So mucus covered muscular membrane is what it is, and the opening between them is called the glottis. And when you make different sounds, the glottis is taking on different shapes a little bit. Although most of the different sounds that we get in terms of like vowels and consonants, those are formed by different stuff you're doing with your tongue and your lips and your how open versus closed and like what shape you're making with your mouth. But then the pitches that we get are formed by passing air through the glottis, and the vocal folds vibrating. And if they vibrate quickly, you get a higher pitch. If they vibrate more slowly, you get a lower pitch. And most men's vocal cords are thicker and a little bit stronger, and it makes them vibrate more slowly, thus giving the deeper pitch that a guy has. But then falsetto, like oh, kind of falsetto, is by adjusting your vocal folds in such a way that rather than having the whole thing vibrate as the air passes by it, the whole thing is overall stationary and just the ridges are rippling basically, and the ridges or edges can ripple much more quickly than the whole thing can vibrate, and so you're able to get a lot higher of a pitch that way. But the tone is different, and you usually can't get as much volume because rather than the whole thing vibrating, it's just the edges that are rippling. And then the trachea. So the trachea would be, it's also known as the windpipe, the trachea that goes from your pharynx, or so pharynx and then larynx and then your trachea goes down to your bronchi. Yeah, so from larynx to bronchi, it's about 5 inches long, and it has these cartilaginous rings on the outsides, like these little ridges that are spaced apart. I don't know, like fairly close together, quarter of an inch, half an inch, and they go almost all the way around, but not quite. They're usually described as being C-shaped rings. But on the inside, it's more ciliated mucus, and the cilia is partially so that if you get like tiny particles of stuff in the air that you're breathing, the cilia help move it back up to the top and then up in around your pharynx again, and then you swallow it and it goes down to your stomach. So the same thing, like dust particles, stuff like that that you inhale in your nasal cavity, it gets trapped by the cilia, and the cilia gradually move it toward the back of your throat, and then you swallow it. So, like snot and stuff like that, the snot is basically the mucus that is covering and trapping the different foreign substances in the air, and then you swallow it to get rid of it. So, that's kind of a pleasant thought, but that's basically what's happening there. And then the bronchi are these two separate pipes that extend out from the trachea, and then each bronchus then branches into smaller and smaller. So each bronchus similar to the trachea in structure, but smaller. And then when you cough, it's usually triggered by an irritated bronchus. And what happens is your glottis, again, like that opening between your vocal cords, it starts out closed, and your lungs force some air up against it to create like a bunch of pressure, and then the cough is your glottis abruptly opening, allowing very quick flow of air up out of your lungs to hopefully dislodge whatever it was that is irritating your bronchus, to go from your bronchus up your trachea and then out your mouth really quickly. That's what's happening when you cough. And then your lungs, each lung has 9 different lung segments, and each one of those segments receives air from a different bronchial branch or a different bronchial tube. And then at the end of each of those bronchial branches, all the way down at the end, they terminate in a bunch of different alveoli. And these alveoli are like microscopic bubble like sacs, and you have approximately 300 million of them in your lungs. And blood capillaries flow to those alveoli, and so that's where the air that you inhaled, the oxygen in it gets absorbed into the blood, and then also like the excess carbon dioxide in the air, it absorbs from the bloodstream into the alveoli, so you exhale some of the carbon dioxide, and then when you inhale the oxygen, it gets into your bloodstream like that. Let's do a video question. Let's do, I kind of have a couple of them here that are coming up. Let's do number 4. If your lungs were laid out flat, so like you took each of these alveoli and you opened it up and laid it out flat, all of these different ones, you open them up, laid it out flat. If your lungs were laid out flat, about what size would they be? And the answer is the size of a tennis court. A tennis court. So yeah, just your lungs. If you laid out all of the different folds, as it were, of your lungs, if you laid them all out flat, it would be roughly the size of covering a whole tennis court. So again, that's video question number 4. And while we're here, let's do video question number 3. Number 3. Although the air is about 21% oxygen, so the air that we breathe is mostly nitrogen, but then the second thing on the list is it's about 21% oxygen. What percent do we absorb when we breathe? And the answer is about 5%, which would put it at roughly a quarter of the oxygen that's in the air, but about 5%. Which again, so 5% compared to the 20% that makes up the air, that puts it at about a quarter of the oxygen is what we actually get into our bodies, as far as like get into our bloodstream when we breathe. And one of the ways that they figure that out is just by comparing the percentage of oxygen in the air that you inhale compared to the percentage of oxygen in the air that you exhale. When we inhale, the air is about 21% oxygen. When we exhale, it's about 16% oxygen, leaving a difference of 4 to 5%. And side note, that's why mouth to mouth resuscitation works because when you inhale, you get about 4 or 5% of the oxygen that's in that air. When you exhale, the air that you exhale is still about 16% oxygen. If you exhale into someone else's lungs, they're getting air that is about 16% oxygen, and their body is able to absorb 4 or 5% of that. And so you are able to get about the same amount of oxygen from breathing what somebody else exhaled as you're able to get from breathing fresh air. Now, long term, there could be, that only works so much, but then long term, there also are issues with carbon dioxide of potentially getting, yeah. Um, don't need to get into that though. All right, let's see. Lungs, we talked about that. We talked about that. Okay, good. Next, the act of respiration. So there are kind of three different ways that respiration is used as a term. There's external respiration, which is just getting the oxygen in the air into the alveoli of your lungs. Okay, so external respiration, just air getting from outside into your lungs. Then there's internal respiration, and that's getting the oxygen from your bloodstream into the cells of your body. And then there's cellular respiration that we covered way back in first quarter. And that is our bodies using the oxygen that we have in our cells for the process of converting food into water, carbon dioxide, and energy. So that would be like glycolysis. Well, glycolysis is technically what you call it, um, anaerobic. So that would be like the Krebs cycle and the hydrogen and electron transport system kind of stuff. And then the act of breathing involves inspiration, which is filling the lungs, and expiration, which is forcing air out of the lungs. And the way that we breathe, the way that we inspire, usually or mainly involves this muscle here, the diaphragm. So what happens is when you inhale, you contract your diaphragm and it flattens. See how like this diaphragm here is more arched and this diaphragm here is more flattened. So the diaphragm flattens, and when it does, it tugs the lungs downward. And what happens is when the lungs are tugged downward, some of this gets into like gas laws that maybe you covered a little bit in physical science, or none of you have taken chemistry or physics yet, so you haven't gotten into them there. But basically, if you have a chamber with air, you increase the volume of the chamber without increasing the amount of air in it, the pressure drops. So when the diaphragm flattens and the lungs expand, the pressure in the air pressure in the lungs is slightly lower, and what that does is it creates or it makes the higher pressure air outside force more air into your lungs. So we kind of think of inhaling oftentimes as like you are sucking air in, but really what you're doing is you're just increasing the size of your lungs, and the atmosphere is pushing more air in because the high pressure atmosphere pushes air to equalize the pressure with the lower pressure lungs that you created when you expanded the size of the lung. So that's kind of what's happening there. And then exhaling, well, there's a little bit with raising the size of with raising your ribs, that also expands the size of your thoracic cavity, thus expanding the size of your lungs. And then exhaling is basically contracting those things to reverse the process. And there you are actively pushing air out of your body. Okay, so that's that. Then different air volumes. There's what's called the tidal volume. And this is the normal amount of air that you inhale and exhale when you're at rest, which is best measured while you're asleep. And for an average person, that's about half of a liter. So the best way that I can think of for describing half of a liter is picture a 2 liter bottle, like a soda bottle. And so half of a liter would be 1/4 of that. So take 1/4 of a 2 liter bottle, and that's about the volume of air that you naturally breathe in and out. But then there's what's called the inspiratory reserve volume, and that's that normal tidal volume plus the amount of air that you can forcefully inspire. In other words, the amount of air that you can additionally breathe in. And that amount of air, so you can take your normal half of a liter and add to it about 2.5 more liters. So in other words, you can, once you do a regular breath in, you can add to that about 5 times the amount of air, right? Because half a liter up to 2.5 liters, 2.5 is 5 times the size of a half. Then you add that half and that 2.5, and you get the total 3 liters there of that inspiratory reserve volume. And that's where getting a deep breath, like when you're singing in choir, makes such a difference because the normal amount of air. Oh, let me put it this way: the amount of air that we get when we get a full breath of air is 5 times, no, a total of 6 times the amount of air that you get when you just do a regular breath in. So huge difference in what good breathing looks like compared to just regular breathing. And then there's the expiratory reserve volume, and that's the normal tidal volume plus the air that you can forcefully expire. In other words, if you get like a full breath of air, that full 3 liters, and then you breathe it out and you stop where you would naturally just stop breathing, you've exhaled 3 liters of air at that point. But then you can force roughly another 1 liter out of your lungs. And then there's what's called the residual volume. That's the amount of air that is left in your lungs after you have forced as much of it out as you can. And that's about a liter that gets left out. So put all these together, and we get about a total of about 4.5 liters of air that, let's see, three, four. See, based on how this is worded, it sounds like this inspiratory and expiratory reserve includes the tidal volume plus, yeah, I'd have to double check exactly how these terms are used because I don't feel like this should be 4.5 liters. But if I assume that the text was accurate with the 4.5 liters, but maybe sloppy with their wording, then I take it as there's a normal tidal volume, and then we can add to that an additional 3 liters. And then from what we breathe out, we can breathe out an additional 1 liter, which then, yeah, would give us 4.5 liters of air that we can possibly inhale and exhale. But then when you include the 1 liter that we can't get rid of, then you get a total of about 5.5 liters. And maybe you've really gotten a sense of this inspiratory reserve if, like, you've ever been sick, like with a chest cold, and when you're getting better, uh, you you might get to the point where, oh, it doesn't hurt anymore to inhale or exhale, and then you do some exercising that involves a little bit deeper breathing, and suddenly it's like you're coughing up mucus that you weren't before, or like you have pain in your chest that you didn't have before, and that's because you're tapping into parts of the lung that maybe are still kind of gunked up from your cold that you didn't notice because the regular parts of your lung that you use when you breathe in and out is so much smaller. Similar thing can happen with people who smoke. Their breath can seem normal with just their regular tidal volume inhaling and exhaling, but then sometimes if they start exercising and they're breathing more deeply, then they can have like small amounts of like sooty, like blackish air coming out. And that's because the like tar kind of build up in their lungs. Those parts of their lungs are getting air inhaled and exhaled that don't usually get inhaled and exhaled with just regular breathing, and so it's picking up some of the tarish soot that is built up in their lungs. Yep. So that's fun. Speaking of smoking, I have a picture here. So this is what healthy lung might look like, and these are what smokers' lungs can look like over time. It just gets just like all this nicotine buildup, and it usually ends up slightly shriveled, and it just can't hold nearly as much air. But then things that can affect your breathing. So first of all, there's a carbon dioxide level in your blood. When you hold your breath, the like growing desire to take a breath is not actually caused by your body saying, I need oxygen, I need oxygen. Instead, what it is it's your brain saying, I need to get rid of carbon dioxide. I need to get rid of carbon dioxide. And is what creates the very, very strong urge to have to take a breath. Because excess carbon dioxide in the blood can be very damaging. So, as a strong trigger to initiate breathing if your body feels like you have too much carbon dioxide building up in the blood. But then atmospheric pressure can also affect your breathing. If you go up in higher elevation, a lot of people say, like, oh, it's harder to breathe up here because there's not as much oxygen. And that isn't really an accurate way of putting it. It's not a matter of excess, sorry, it's not a matter of low carbon dioxide. If you compare the amount, sorry, low oxygen, if you compare the amount of oxygen at high altitude versus the amount of oxygen at sea level, the oxygen quantities are in the air are essentially the same. What is different is the atmospheric pressure. And remember earlier we said that when you are breathing, when you inhale, you increase the size of your lungs and the atmospheric pressure pushes more air into your lungs. Well, if there's less atmospheric pressure, then less air gets pushed into your lungs. And so it isn't a matter of less oxygen in the air, it's a matter of when you inhale, less air gets into your lungs because the air outside is lower pressure. But people who train up at higher altitudes, their body ends up getting acclimated to that. And mainly what happens is it's not so much that like there's some kind of physiological change that creates like a lung capacity that gets more air into it, but rather your body adjusts in how much oxygen it absorbs from the air that it gets. And that's mainly what changes. And so that's where a lot of athletes will do higher altitude training because their body gets more efficient at getting oxygen out of the air that they breathe so that when they go and compete down at sea level, their body is able to perform better under strain because it's getting more efficient absorption of oxygen from the air. That's also things like the Colorado Rockies and the Denver Nuggets, pro baseball and pro basketball teams. Their teams have a little bit of a home field or home court advantage because they play so regularly higher altitude that other teams who come and play there, oftentimes the players feel out of breath more quickly because they're not as used to competing at high altitude because Denver is roughly a mile high in elevation. And then other things that can affect your breathing. Severe pain can cause you to take a gasp of air, a sudden feeling of cold temperature, like if you jump into cold water. I remember swimming in Lake Tahoe one summer. I mean, it was summertime, but Lake Tahoe was largely fed by ice melting. Um, and a guy that we were with had a digital watch that had a thermometer on it, and his thermometer was reading a water temperature of 36 degrees, I think. And yeah, when you jumped in, you couldn't breathe for a second, and that's an effect of feeling sudden coldness. Your body kind of stops breathing for a moment. And then just how good a physical condition you are, what your body size is, what posture you're in, what your age is, all those things affect breathing. The normal breath rate starts out very high when you're a child, and as you get older, your your resting breath rate, uh, so how many breaths you take inhaling and exhaling per hour or per minute, depending how you're measuring it, your rate of breathing gradually slows down as you get older. And a brief note about carbon monoxide poisoning. So you've probably heard things like don't have a car running in a closed space like a garage because of a danger of carbon monoxide poisoning. So carbon monoxide is similar to carbon dioxide, but it's a carbon and one oxygen instead of a carbon being bonded to two oxygens. And the reason why carbon monoxide poisoning is so dangerous is carbon monoxide bonds with the hemoglobin in your blood approximately 200 times stronger than oxygen bonds to hemoglobin. So when you inhale some carbon monoxide, it basically locks up those hemoglobin molecules in your blood so that they can't transport oxygen anymore. Then what happens is your body senses, oh, I'm not getting the oxygen that I need. Quickly increase the rate of breathing and increase the rate of heart beating to get more blood circulating and more blood getting air. But then what's happening if you're still breathing carbon monoxide? You've just increased the rate at which more of your hemoglobin molecules get bound up or locked from being able to transport oxygen because they are being preoccupied with carbon monoxide instead. And then what ends up happening is essentially the same as being strangled is there's a lack of oxygen flow to your brain, which then makes you pass out. And then now that you've passed out, you can't get away to a safe place. And then your organs just start to shut down from a lack of oxygen. So, yeah, that's fun. Okay, a little video. Hopefully it plays. If not, I'll post it as a separate link. Just a quick overview of. Oh no, wait. This one is looking at some lungs. That's right. And this, I'm pretty sure it says, but uh, different science labs sometimes will use cow lungs. Usually, it's like bought from a science supply company. This lady got some from a butcher, and cow lungs to show what inflating and deflating of a lung looks like. But then it also goes into a little bit of other stuff about your respiratory system.
Now for a spectacular biological hack. Rachel Peterson from Washington State wanted to show her kids how lungs work. So she purchased some cow lungs from her local butcher and attached a leaf blower.
Lungs just look weird. But then again, I guess they weren't designed to travel around without the rest of the cow attached.
Some people might think this looks a little bit gross to see these lungs being inflated on the table, but to me as a biologist, I think it's amazing to see how this organ really works.
When a cow breathes, it's taking in oxygen through its bronchial tubes. And it goes through the bronchial tubes and into the lungs and into these tiny, tiny little tubes called alveoli. And the purpose of the alveoli is to increase the surface area where gas exchange can take place.
We're talking up to 500 square meters of surface area within a lung. And this is to be able to transfer oxygen into the tissues and to allow CO2 or carbon dioxide to transpire out of the tissue. So surface area is really critical in the lung.
So Rachel's leaf blower replicates breathing on a table. But these lungs look like they could burst. Would they ever really get this big?
An ordinary breath for a cow is about 1 gallon of air, or 5 liters. But when you take the lungs outside the body and attach this leaf blower, you can inflate them to about 4 times that size.
Now that's some serious lung-busting science that you'll only find in the Hackiverse.